talk about the angular size of objects. In an astronomy class, the angular size of something is pretty readily measurable. If you know something intrinsic about like how big the object actually is, the angular size will tell you how far away it is, or vice versa. If you know how far away it is and you can measure the angular size with your telescope, then you can figure out how big the object actually is. So it works in both directions, and it's relatively straightforward to measure basically how much of the sky is covered by a given object. So the scenario we're thinking about is that I have some object, it has some physical diameter, and it is some physical distance away from me, and on the sky it's going to cover some angle theta. We can set up ratios, so the angle theta over a full 360 degrees to go around the circle. So that ratio of theta to 360 degrees has to be the same ratio as the physical diameter to the full circumference of the circle. So physical diameter over circumference, and circumference is 2 pi times the radius. The radius here is the physical distance. And the word physical is just meaning like actual measured values in meters, for example. Okay, so I have a 2. I can simplify this equation. I'm going to multiply both sides by 2. And when I do that, that 2 will cancel out, and this will become 180 degrees. So let me rewrite that. So theta over 180 degrees is going to be the physical diameter over pi, the physical distance. And solve for theta by itself, multiply both sides by 180 degrees. We'll have theta is 180 degrees over pi. And then I'll have this ratio of the physical diameter, so how far across the thing actually is, to the physical distance, how far away the thing actually is. Okay, so a few things to note about this. I've gone through it to show you where the 180 degrees over pi comes from, so it's hopefully less of a mystery. These units will hopefully cancel out. Pi is a pure number, so the only thing that has a unit over here is the 180 degrees. So we expect to have theta in degrees. Something that filled my entire field of view, so all I could see was that object, would have an angular size of 180 degrees. So an angular size of 180 degrees means object fills your entire field of view. So theta has to be less than or equal to 180 degrees. You can never have it be bigger than 180 degrees. So if you go through a calculation and you come up with an angular size of 2 million, you're definitely wrong. There is no possibility, because something that fills your entire field of view is just 180 degrees. The other thing to note is you want to make sure your physical diameter and physical distance measured in same unit of length. So their ratio, the units could cancel out and you would get a pure number. If my diameter is in meters and my distance is in light years, then I will wind up with a meter over a light year, which doesn't cancel out. It's off by quite a bit. So when you're setting up an equation using the angular size, make sure you've converted the physical diameter and the physical distance so that they're in the same unit of measurement. I don't really care what that unit is. If you like furlongs, use furlongs. If you like miles, use miles. If you like meters, use meters. But it has to be the same for both the numerator and the denominator, or else you're going to have units that don't cancel out. Alright, so a little bit more about angular size before we dive into example. So a degree on the sky is actually pretty big. The moon and the sun are each about a half a degree in the sky, and those are the biggest things that you can see in visible light. There are bigger things on the sky, but you're not going to see them with your eye. So sometimes we're going to want to use a unit to measure an angle that is smaller than a degree. And we have two of those that are in fairly common usage. There is the arc minute. 1 degree of angle is equal to 60 arc minutes. So a single tick mark means arc minute. And then there's a smaller unit to measure angle called the arc second. And 1 arc minute of angle is equal to 60 arc seconds. So the double tick is telling us arc seconds. Make a little note. Arc minute and the double tick means arc second. All right, so let's try an example. So what is the angular size of the sun as viewed from Saturn? So we're going to flip into the appendix of our textbook and look up a couple pieces of information that we need to answer this. The physical distance is the distance from the sun to Saturn, and we write that out in decimal form first. 1,427,000,000, and that is in kilometer. So 1,427,000,000 kilometers away. Again, that's going to be sort of crazy to keep writing out all the zeros. So lazy scientist raises his head and says, let's write that in scientific notation. So 1, 2, 3, 4, 5, 6, 7, 8, 9. 1.427 times 10 to the 9th power kilometer. And then we also look up what is the diameter of Saturn, so ignoring the rings, just diameter of the sun. Because we're looking at the sun from Saturn. All right, and that is 1,390,000 kilometers. And again, let's write that in scientific notation. 1, 2, 3, 4, 5, 6. So 1.390 times 10 to the 6th. All right, so we have a physical distance, we have a physical diameter, and they are both in kilometers. So we're good to go. So what's the angular size of the sun as seen from Saturn? So the angle theta is going to be 180 degrees over pi. The physical diameter, 1.390 times 10 to the 6th kilometer over 1.427 times 10 to the 9th kilometer, and the diameter and the distance are both measured in the same unit of measurement, so kilometer cancels out in numerator denominator, and then this term in parentheses is just a pure number. Carry out that calculation, we're going to get 0.056 degrees, and that degrees is coming from the degrees in 180 degrees. And that's a pretty small angle, not necessarily like useful. Don't necessarily think of like how small that is. So I'm going to change units on it, and instead use the next smallest measure of angle, so 1 degree over 60 arc minutes, to change units from degrees to arc minutes. It's going to give me 3.3 arc minutes. And that's about 10 times smaller than the sun is in the sky for us, which makes sense. Saturn is about 10 times further away from the sun than we are.